Well, good morning, everybody, and welcome to cup number 6 of Cosmic Coffee from here at Lowell Observatory. Very nice to have you with us this morning. I'm Jeff Hall, the astronomer and director of Lowell, and I'm here tonight with our deputy this morning, actually, with our deputy director for science, Michael West. Now, the first thing we do on Cosmic Coffee is give a little shout out to one of our local small businesses. So this morning I'm having a nice dark blend from Matador Roasting Company down there on Milton and right at the intersection of Milton and Clay. They have a nice drive-through. You can go get a good cup there and support your local business. Now, previously on Cosmic Coffee, we've covered this or that kind of topic. Today, we thought we'd do something a little different and do a survey of the entire universe from its smallest structures to its very largest. And each slide of the presentation will be kind of stepping out by one or more powers of 10. Some of you may have seen the old movie of the same name, which is kind of a continuous zoom out through the universe. We're not going to make this absolutely continuous. We're going to jump around a little bit just to give you an idea of some of the relative sizes and scales throughout the universe. Now, I'm going to go ahead one slide here and sort of introduce things by pointing out how many powers of 10 we're going to have to go through. And here you see this number. In mathematical parlance, we would call this a BFN, right? So it's 45 powers of 10. That's a tremendous range of scales. We're not going to do all 45 because that would take forever. So we'll go through some of the main ones and just say a little bit about everything we encounter along the way. So moving ahead to our very first scale, every slide is going to be set up exactly the same way. So we'll show you how big this white box is in 3 different ways. You can see exponential notation at the top, or the metric prefix name at top right, and then at bottom decimal notation, and then a little scale at the bottom with the arrow showing where we are in the powers of 10. Now down here at 1 atometer, this is really not very large. And we're looking at what is, of course, not a photograph of a quark here.
Yeah, I mean, for me, I think it's always interesting. Astronomers and physicists talk about these incredible scales from incredibly small to incredibly large and pretend like we know what they mean. But, these are just scales so far beyond our daily understanding, right? I struggle to, understand how far a mile is when I'm driving. But we're sort of at the scale of quarks here, like you said, Jeff, and those are the building blocks of atoms in a sense, right? It used to be people thought, well, atoms are made of protons and neutrons and electrons. In fact, the Greek word protos, which means first, is the origin of the word proton. But we now know that, in fact, quarks are even smaller, more fundamental particles that make up atoms on these unimaginably small scales. The thing I always remember, too, is the person who coined the term quark was Murray Gell-Mann, who was a famous physicist, won the Nobel Prize. And he chose this word after reading Finnegan's Wake by James Joyce. So to me, I always like the sort of connection between science and literature and the humanities. And Gell-Mann was a great example of that, choosing this name for the tiniest subatomic particles we know of.
For sure, and then giving somewhat whimsical names to the different types of quarks, right? We have up, down, top, bottom, strange, charm. So yeah, go look that up. Now the interesting thing is, right off the bat, we're going to have to take a jump for the next slide of a factor of 1,000. So we just did 3 orders of 10 to get to the proton you were just talking about.
Yeah, and protons, again, everything that you see around you, right, is made up of protons and neutrons and electrons. And so we think that's really common, but in fact, we're the weird stuff in the universe because protons and neutrons and electrons make up only about 5% of the stuff that exists. We think most of the universe is made up of dark matter and even more dark energy, and that's not you and me, so we're kind of the oddballs of the universe in that sense. Now, these protons and things like this were created in the first few minutes of time after the Big Bang. The universe was so hot that energy, photons, were able to transform into matter. Everybody knows E equals mc squared, and energy and matter are equivalent. And so the intense heat and light in the few moments after the Big Bang actually created things like protons.
Yeah, and so right, and so these subatomic particles, as you said, are kind of the fundamental constituents of atoms, and that leads us to the biggest single jump we have to make in our scale tour. We're actually going to go now by a factor of 100,000. Now, if you look at this slide right here, you'll see the box representing 1 femtometer, and then right down at the lower right of it, right in here, a little teensy box. This is sort of supposed to represent the box from the previous slide. Now, of course, if I really did that to scale, it would be smaller than a pixel. So imagine there's just 3 little quarks make this up, and they're in there. And now to get to an atom, we're going to have to go forward right here to 10 to the minus 10th meters, roughly. This is about a tenth of a nanometer. And so that's a factor of 100,000. And we're seeing what, Michael, what might not look like our traditional view of an atom here.
That's right. That's the idea, there's this cloud of electrons. Many of us in school learned the Bohr model of the atom, right, where electrons move around the nucleus like planets around the sun, and that's not really the case anymore. For me, I always think, we all learned in school, like I just said, that, everything's made of atoms, and it's sort of common knowledge, obviously, but it's a really fundamental discovery, right? I always remember the quote by Richard Feynman, Nobel Prize physicist, who said, if civilization was destroyed and only one message could be passed on to the future, what would convey the most information in the fewest words? And he said it would be that everything is made of atoms. That is our greatest discovery, essentially, right? So I think we take it for granted, but it's incredible that we can see and understand things so far beyond our scale of our day-to-day existence, right? Whether that's the existence of atoms, the existence of dark matter, existence of all these different things. It's pretty incredible that we can figure this out.
Yeah, it's wonderful that the understanding that we've built up, and I totally agree. That comment of Feynman's, if you just sit back and start thinking about it, it's right up there in the very first of his famous lectures on physics, and it's a profound statement. And of course, what we're seeing here is sort of a quantum mechanical interpretation of the atom, where the electron isn't that little planet; it's kind of a cloud of probability, and that leads to some just mind-bending and mind-expanding concepts. It's fascinating to study. So now we have to take yet another jump of a factor of 3 and powers of 3, and this is going to take us to a site I think all too familiar these days, right?
Yeah, unfortunately.
Yeah. So
sorry, go ahead.
No, go ahead.
No. So I mean, of course, the world is dealing with this pandemic, and it's sad and incredible that something so tiny like this, again, something that you can't see with your eye, is creating such havoc around the world. It's just tragic.
Yeah, right. And this is kind of an estimate. I looked this up online, so how big actually is this thing? And we're kind of up around a little less than 100 nanometers, or a tenth of a micron now, as you can see the terminology on the slides changing. So we're these tiny particles, and at the sort of the next 2 powers of 10, now we're going to start getting into things that have real visible impacts on our observations. And these are things like interstellar dust. So if we look at the scale of either 1 micron, and you can see that the little coronavirus down there, because we've only gone out by a factor of 10, so that's scaled to the right size. And then slightly larger dust grains, sort of in the 10 microns area. So this is pervasive throughout the universe.
That's right. I mean, I always remember there's this great poem by William Blake where he talks about seeing the world in a grain of sand, right? And in a sense, you're seeing the history of the universe in grains of dust like this. I mean, these are the ashes of dead stars. And we didn't realize this until the 1930s. There was an American-Swiss astronomer named Robert Trumpler who realized that distant stars appeared fainter and redder than they should. And he inferred from this that space was filled with these little tiny dust particles like you see in this image, and that they would block some of the light and redden the light from these distant objects. So I think that was a pretty incredible discovery. And we know that this stuff is everywhere. It makes it hard for us to see very far in our own galaxy. It's like looking through a thick fog or looking into the smoke from a forest fire. You can only see so far, and that's what this dust does to us.
Yeah, right. If you look at those famous all-sky pictures of the Milky Way, you see those dark, patchy areas running through it, and you're just seeing enormous collections of this. And now we're actually getting up to the point where we can start to see stuff, because when we get up to about here, 1/10 of a millimeter, we're getting close to the resolution of the eye. And here we're looking at an electron micrograph of a human hair.
Yeah, the thing I always remember is just to sort of compare scales. If you pluck a hair from your head and held it at arm's length, it would cover thousands of galaxies on the sky, right? That little width of your hair would cover thousands of galaxies. So it just shows, how many galaxies there are in the universe and how rich it is. The other thing is just to make a connection with hair. The word comet actually comes from the Greek word for long-haired or hairy, because they thought comets with their long tails were hairy stars, essentially. And of course, when you see things like the Lyrid meteor shower last week, you're seeing little grains of dust, like we just talked about, burning up in the Earth's atmosphere. But yeah, as you say, Jeff, it's nice that this is the first thing you can actually start to see with your eye.
Right. And I love that association. Of course, comets were widely regarded as, omens and harbingers of doom. And the other word association I've always kind of liked that goes with the hair business is just disaster, right? It's just disaster, which is a bad star. And we have these associations are baked into our language. Now, you mentioned shooting stars. If we go up one more power of 10, here we are. So the box is now a centimeter. So this is something we could easily see and measure. And here I've just sort of dropped in a little particle that's probably a millimeter or less. And this is probably your basic shooting star.
That's right. Those are the things you see burning up in the air, right? On most nights. I mean, obviously, from time to time, there's something bigger, and occasionally something even lands. But generally, those things are, about that size. They're not very big at all. But of course, they heat up as they roar through the upper atmosphere at high speeds, and they glow, and that's what you see as a shooting star.
Right. So now we will jump to some slightly different kinds of objects here. We're going to jump up by another factor of 100 and look at something that is around the size of a meter. And this is the new Dyer telescope, which we installed here at Lowell Observatory, thanks to a very generous gift just before we had to shut down. So here's this beautiful plane wave telescope with an aperture of a little less than a meter.
Yeah, and the idea is, of course, astronomers like to build telescopes as large as possible because they collect more light that way. And a 1 meter telescope for public viewing is a fantastic instrument. The biggest telescopes in the world, of course, the biggest optical telescopes at least, are roughly the 10-meter size. The biggest ones are actually the GTC, the Gran Telescopio Canario, Canarias in Spain, in the Canary Islands. The mirror is 10.4 meters in diameter, so it will collect roughly 100 times as much light. But obviously, the bigger the telescope, the more light it collects, but the more expensive it gets too, of course.
Well, okay, so let's talk about expense, because if we go up by a power of 10, from 10 to the 0 meters to 10 to the 1, we can see one of those somewhat larger telescopes. I've tried to kind of scale this picture, so the mirror in there is around 4 meters.
Yeah, so that one would collect, about 16 times as much light as the 1 meter telescope we showed previously. This is a great instrument for studying the universe, from objects in our own solar system, comets, asteroids, to distant stars, to mapping the Milky Way, to studying the most distant objects in the universe, like galaxies and quasars and things like that. It's incredible. And the other thing people often forget is telescopes are time machines, right? You're looking back in time. When you look at an object, when you look at the sun, you're seeing it as it looked 8 minutes ago. When you look at other stars, other galaxies, you're seeing as they looked thousands, millions, even billions of years in the past. And it's really incredible when you think about it that we can look back in time. There aren't many sciences that can do that.
Yep, and fortunately, I'm remembering at this point that so far neither of us has managed to say the name of this telescope, which we certainly want everybody to know. This is the Lowell Discovery Telescope, and I think to your point previously, Michael, about the complexity of these instruments, the 0.67 meter Dyer telescope, in very round numbers, costs about $100,000. This telescope was $53 million for basically 4 times the aperture.
The thing that always impresses me, I've been at probably every major telescope around the world practically, and every time you walk in, it's like walking into a church. It's like walking into a cathedral. It's just beautiful, and it's awe-inspiring. And no matter how many times you walk in, you see these giant telescopes that move so silently, and they harvest the light right from the past. It's just a really moving experience. I find it's like I always say it's like walking into a baseball stadium. Just this sense of awe and majesty, and that's how you feel when you walk into a telescope.
Totally. And you know, all of the great instruments, you know, you walk into the huge 200-inch telescope dome at Palomar, for example, and, you know, it's just a miracle of engineering. All right, so one more telescope, we can go up 2 powers of 10 now to a kilometer, and now we can see yet another kind of telescope.
Yeah, so this is an interferometer, right? This is NPOI, the Navy Precision Optical Interferometer, out on Anderson Mesa, about a half hour outside of Flagstaff, that Lowell Observatory operates with the Navy as well. And it's just an incredible facility. Remember we said a few minutes ago, the bigger the telescope, the more light it's able to collect.
Right.
And that has 2 advantages. The bigger telescope lets you see fainter things, but it also lets you see more clearly. It gives you sharper images. But making an enormous telescope, you know, with a mirror hundreds of yards or meters across would be impractical. So what an interferometer does is it kind of takes the cookie cutter approach. What would be a single large mirror, difficult or impossible to make, you make it out of little pieces instead, and then you combine the light from all of them. And what you can do in that way is you can get about the same resolution. You can see about as much detail as you could as if you built a single dish. And so that's what this telescope does. And interferometry is used, for example, that's how the first image of the black hole that you probably saw last year, this supermassive black hole in the galaxy M87, that was taken using an Earth-sized telescope where they linked together radio telescopes from around the world to give the resolution needed to see this black hole.
Yeah, that was a fabulous achievement. This gets us to scales now where, as you can see here, we're clearly in an aerial photograph. I actually screenshotted that with Google Earth. And of course, the interferometer itself is this big Y-shaped thing with the little mirrors along the arms, as Mike was talking about. Then we got a couple of other domes out there. This is a site Lowell Observatory has operated under a collaboration and use permit with the Forest Service since 1960. So now we're in the air, and now we really are getting out into space as we start to go up to these larger scales. So some of the initial scales kind of happen right in our solar system. So here we've jumped up to looking at a megameter, or about 1,000,000 meters, and we start to get to moons. And here we have Enceladus, which is a neat little moon of Saturn.
Yeah, and there's several moons in the solar system, right, where we think that there could be life even, or conditions for life. There's possibly Titan, there's Europa, and although you think, well, it's really cold way out there far away from the sun, and it is, but there could be other sources of energy too. And I think one of the things that always amazes scientists is just how robust life is on our own planet and the extreme range of conditions that it can survive and even thrive in. And so, whereas in the past we would have said, oh, you'll never find life on places like this, way too cold, way too far from the sun. Now it seems like you could. There's liquids like liquid oceans. Mm-hmm. You may have heat sources like underground volcanoes and vents, and so it's actually quite plausible that life might exist on these sorts of moons.
Yeah, and fabulous that of all the generations of humans, we are the ones who are at the point where we have the technology to detect and even visit some of these places. I mean, in our own solar system, there are missions that have gone and are planned to go to these worlds. And of course, now we're getting the technology even to look for life around other stars. Now,
some of the images from Titan and whatever, it's incredible, right? You know, when the Huygens craft actually descended through the atmosphere, and you see pictures of lakes, and it's just incredible.
Yeah, and now there's this incredibly neat mission on the books to go back there and basically fly a drone around and really do more exploration. Just a really cool idea. But
Titan's atmosphere is almost as thick as the Earth, so it can actually support a drone flying.
It's actually pretty, and it's so cold, it's pretty dense and mushy, and actually fairly easy to navigate around in. Our own moon, we have to go up another power of 10. And so now you can kind of see relative scales. Enceladus is a fairly small moon. Our moon is pretty sizable among all the moons in the solar system.
Yeah, the Earth and Moon are often called a double planet system, right? Because the Moon is pretty big relative to the Earth. If the Earth were hollow, you could fit about 49 moons inside of it. For me, the interesting thing is, we talk about social distancing these days, and the Moon has been doing this for a long time. It's slowly moving away from the Earth at about 1.5 inches per year, or that's almost 4 centimeters. And as it does, it's slowly stealing rotational energy from the Earth. And so days are slowing down. If you were around when the dinosaurs walked the Earth, days were about 3 hours shorter than they are today. So I always find that really interesting that the Earth is moving away. Sorry, the Moon is moving away from the Earth. The other thing is interesting. We talked about the coronavirus before, and for many of us, it's an interesting challenge working from home or not being able to go out anymore or whatever. When the astronauts landed on the Moon and they came back, the Apollo 11 astronauts, they were quarantined for 3 weeks out of concern that maybe there were viruses or other microbes or harmful things that they could have brought back from the Moon with them. So quarantine and the Moon are not unknown to each other.
Right. So from 10 to the 7th meters, we can go up another factor of 10, and this takes us from moons into the realm of planets. And so there's our moon in the little box at lower right, and a very familiar sight that we love showing people here at Lowell when we can be open.
Yeah, Saturn. I mean, I always say the 2 most interesting things you can show people in the telescope are the Moon, because the craters look amazing, and Saturn, because the rings are unbelievable. I'm sure you've had this experience, Jeff, where people will think it's fake, right? It's a fake image of Saturn because it looks so good through the telescopes. And for people that are listening, if you've not been out to Lowell yet, when we reopen, come out and look through the Godo. It's our open deck observatory, Valley Open Deck Observatory. The views through the telescopes you have out there are phenomenal, and Saturn is one of the nicest things you could possibly look at. Yep.
Saturn through the 8-inch moonraker refractor is, it's very common to say, oh, you stuck something on the lens. It's pasted on there because you can see this with such crystal clarity. The rings are obvious through a good telescope like the moonraker. You can see the shadow of the rings, if the geometry is right, lying on the planet, and it gives it this 3D look that's just magnificent. One more power of 10 to a gigameter now, 10 to the 9th meters, and we're getting up to the size of our sun. So there's the sun compared to Saturn, which is, almost 10 times the size of the Earth. And the sun's kind of a run-of-the-mill star.
Yeah, well, it's one of your areas of research, Jeff, of course.
Yeah.
The sun is, again, it's kind of mind-boggling for humans. To give you perspective, I said earlier, you could fit about 50 moons inside the Earth. You could fit about 1 million Earths inside the sun, right? It's just enormous.
Right.
We talked about time before, too. One of the things I always find most interesting about the sun is when you look at the sun, we say, well, the light took 8 minutes to travel from the sun to your eyes. That's true. But that light is already probably almost 1 million years old because the light that's created at the center of the sun struggles to escape. It bounces into other atoms and other subatomic particles on the way out, and it takes it as much as 1 million years to escape the sun. So the light you're seeing is actually quite ancient already.
That's right. After being generated deep in the core, it sort of works its way out, and then all of a sudden gets to a layer where it suddenly becomes kind of transparent, and that's what we refer to as the surface of the sun, even though it's kind of a plasma that's tens of thousands of times less dense than air. Now, the sun looks huge, but to talk about the largest stars, we can go up another 2 powers of 10, and actually we're going to talk a bit about the topic of cosmic coffee number 1, which is the star Betelgeuse. And at this point, remember, the sun is now down in that little tiny box at lower right, so this thing is a monster.
Yeah, if I remember right, if you plunk Betelgeuse in the middle of our solar system, it would extend way out past Jupiter or something. It's just enormous, right? And again, I think that's the incredible range of sizes. If you think about the largest human being that ever existed and the smallest human being that ever existed, it's several factors in difference, but the enormous range of sizes among stars is just incredible. And a star like Betelgeuse is one that's far, far bigger than the sun, and there are other stars that are far smaller than the sun as well. Like Jeff said, like you said, Jeff, it's a pretty Our sun is a pretty run-of-the-mill star, but there are some enormous beasts out there.
There really are, and we're going to start adding a little bit of terminology up there in green at the top of the box. So we're technically at 1 terameter. That's what we would call 10 to the 12th meters. But I also note this is about 6.7 AU, or astronomical units, which is the distance from the Earth to the Sun. And as you said, Michael, I mean, Jupiter is 5 and change, and so this thing would extend out past Jupiter. So Mercury, Venus, Earth, Mars. I mean, you think it sort of makes the coronavirus issue kind of pale in comparison if you were to move Betelgeuse into the solar system. And if we zoom out another factor of 10, there's Betelgeuse down in the box, and now you can kind of see the entire solar system, including this enigmatic region we call the Kuiper Belt.
And I think that was the interesting thing with the discovery of Pluto at Lowell Observatory, for example, the fact that the solar system was far bigger than we used to imagine as well, right? We'll talk about the Oort cloud later, but it just extends so far out there. But again, just to give you a perspective about the distances, we said a minute ago, light takes 8 minutes to travel from the sun to the Earth. It takes 5 hours to reach Pluto, right? It's way, way out there. Yeah. And so, there's much to explore still in the outer regions of the solar system. And that's what things like the New Horizons spacecraft are doing at the moment.
Which, of course, is a significant challenge for all the men and women who made New Horizons happen. If you wanted to do something, you got to have that plan several hours in advance as the instructions propagate out there. So you mentioned the Oort cloud. That was a jump right there of a factor of 1,000, 10 to the 13th to 10 to the 16th. We're now talking about petameters, or here's a box roughly a light year across.
Yeah, so to put it in perspective, we said a minute ago it would take 5 minutes from the sunlight to reach Pluto. To reach the Oort cloud will take weeks or months, even years, to reach the outer edge of the Oort cloud. And what the Oort cloud is, for people that might not know, it's this region in the very, very distant part of the solar system, actually getting a significant part of the way, the distance to the nearest star, Proxima Centauri, and it's made up of trillions of tiny icy objects, the nuclei of comets. Occasionally some get dislodged and come racing in towards the sun, and we see them. But I think this is sort of the repository where the vast majority of comets hide out.
Right. And now the numbers are, for the last part of the tour here, are going to get kind of mind-boggling, because from 10 to the 16th, we're going to go up a factor of 10 to 10 to the 17th. And this is kind of a 3D representation of the stars in the solar neighborhood when we look at a box 10 light years across.
Yeah, and as you say, the nearest star to us is Alpha Centauri or Proxima Centauri, yeah, and that's about 3 light years away. And most of us don't think in light years. So to put it in perspective, if you could get in your car today and drive to the sun, 60 miles an hour, not stopping for donuts or anything on the way, it would take you 177 years to drive to the sun. To get in that same car and drive to the nearest star, Alpha Centauri, it would take you 50 million years of nonstop driving. And that's the nearest star to us, right? So a picture like this that shows our solar neighborhood, keep in mind, our solar neighborhood is still mind-bogglingly huge, and this is just our little tiny backyard in the Milky Way galaxy.
Yeah, and I'm using the mouse cursor here to point out there's Alpha Centauri. If the sun is right there, you have Alpha Centauri. Over here, this big star Sirius is the brightest star in the sky other than the sun. There's a little pair over here that is of great interest to me. They're pretty nondescript, and they have the thrilling name of 61 Cygni A and B. But those are 2 of the stars on our long-term stellar activity cycles program. We used other stars like the sun to sort of understand how the sun itself behaves. So from the solar neighborhood at 100 petameters, now what did we just do? We did another factor of 1,000, 100 exameters, or 10,000 light years, and now we can start to see a bit of our galaxy.
Yeah, and again, it's really challenging. As we said earlier, there's all this dust out there which blocks our view. It makes it hard to see very far. It's really like trying to see the forest for the trees when you're stuck in the middle of the forest. And yet, slowly but surely, over the past century or so, astronomers have pieced together a map of what our galaxy looks like, and what the larger and environment around our sun looks like. And so we see, for example, there's evidence of these spiral arms we talk about.
Yeah.
And our sun seems to be near the edge of one of them. But yeah, the sun, again, astronomy is very humbling. You start to realize our sun is just one of countless other stars out there sprinkled through space in certain patterns or whatever. And, the more we map the universe, the more humbling it becomes in some ways.
It sure does. And it's to your point about it sort of being inside the forest and trying to understand it, in many sort of areas, it's actually easier to study what's going on in other galaxies than it is what's going on in our own. And in some ways, there are some stellar parameters. It's actually easier to characterize for other stars than our own sun because it's so close and so bright. It makes it hard to figure these things out.
That's a good point.
So
where do we can know more about the distant universe and distant stars than you can about our own local ones sometimes.
So from 10 to the 20th, 10 to the 21st, now we have this interesting everyday word. If you take nothing away from this show, I think here's something, you can talk about stuff in terms of zetameters now and impress your friends. So now we see the whole galaxy, and instead of light years, I'm switching units to parsecs. And so this is 30,000 parsecs, and a parsec is a little over 3 light years.
Yeah, another way to put it in perspective, so the Milky Way, if you could take one of the white blood cells from your body, and that represents the sun, then the Milky Way on that scale would be the size of the United States. It's just enormous, right?
Yeah.
Another way to think of it is if you could clone the sun and lay suns end to end from one end of the Milky Way to the other, you need almost 1 trillion suns to go from one edge of the Milky Way to the other edge. It's just enormous, right? And so there's so much of the Milky Way that we haven't mapped, and it's difficult for us to map it because of all of this dust, the stellar dust that's out there. The other thing you notice in this picture is it shows this elongated structure in the center of the Milky Way, and that's what we call a bar. And so we believe today that our Milky Way is one of a type of galaxy, a spiral galaxy. You can see the kind of beautiful spiral or whirlpool pattern, but it's also got this kind of bar structure in the center, so we say it's a barred spiral galaxy.
Right. A very beautiful structure to, when you look at other barred spirals in the universe. And as we start to do the final zooms here, we're going to be talking pretty much about galaxies. Here's our galaxy. Another factor of 100, we're up to 3 megaparsecs, or 3 million parsecs. And at that distance, we're seeing the entirety of what we call the local group, with 3 big galaxies and then a whole bunch of little ones.
Yeah, we basically, galaxies are very, very gregarious. They like to hang out with each other. It's really rare to find an isolated galaxy. And so we live in sort of the equivalent of a village that astronomers who are not very clever with their names call the local group. And it has, like Jeff said, there's roughly 36 galaxies. The Milky Way is the second biggest one. But it's not the most densely populated part of the universe. There are far more dense regions where they're almost like cities of galaxies, like the New Yorks and Tokyos of galaxies. We're kind of in a little bit of a quiet suburb.
Yeah, we're this is like the Flagstaff of galaxies here, I guess.
Yeah, pretty much.
And now we can, but we're going to see some of those cities when we go from 10 to the 23rd to 10 to the 24th. This is sort of a map of the local supercluster, and we've got this, we're looking at 1 yottameter. Who knew?
Yeah, so something like you see the Virgo cluster in that image, for example, and that's kind of the nearest big city. So to use your analogy, Jeff, if Flagstaff is the local group, then the Virgo cluster would be Phoenix, basically. It's a big city, and it's not that far away. And it's enormous. It's got thousands of galaxies all held together by gravity, all dancing around each other in constant motion. And that's about, as you say, 30 megaparsecs or so away on the scale. The Virgo cluster is about 50 million light years away. So if you go out and look at galaxies in the Virgo cluster, which you can do tonight if it's clear and you have a telescope, you're seeing light that's traveled for roughly 50 million years to reach your eye tonight. Right. And this is a nearby part of the universe still.
I know. This is, if you're talking about megaparsecs, which is an immense number, it's still the nearby universe. So at 10 to the 25th meters, 300 megaparts, now we're starting to see even larger superclusters of galaxies. The clusters themselves are clustered into superclusters.
Yeah, we see that. This is one of my own areas of research, is what does the universe look like on the largest scales. And we see that galaxies are not sprinkled at random through space. they clump together, not just to create these little villages and cities of galaxies, but even larger, enormous structures, all kind of linked together in something that we call the cosmic web. And we identify some individual things we call superclusters, like Laniakea, for example, which I think you can see in that image. Laniakea is a supercluster of galaxies. There's almost 100,000 galaxies estimated to be, and the Milky Way is sort of an outlying member of that. There was another equally large supercluster discovered a couple years ago, Saraswati, which is named after a Hindu goddess, which also has hundreds of thousands of galaxies. And the incredible thing is, when you think about it, we now believe that these enormous structures, these mind-bogglingly big structures, began from tiny fluctuations, tiny irregularities in the distribution of atoms in the early universe that gravity amplified over the last 14 billion years or so to produce these enormous structures that we see today.
Right. And when we try to sort of map the grandest scale of those structures, we're kind of now, this is a computer simulation. It was not actually generated to simulate the scale we're showing, but it sort of represents some of the largest scale structures. This is our final slide. We're looking at a box of about 15 gigaparsecs, about roughly the size of the observable universe. And there's this incredible filamentary look to it.
That's right. And it's called the cosmic web. And as you say, Jeff, it is this very kind of filamentary distribution. It almost looks sort of gossamer-like. And we think we understand pretty well why the universe appears this way. We see this observation. If you map the distribution of galaxies in space, I would say astronomers are almost like cartographers. We're mapping things. You find this kind of filamentary pattern. And if you do computer simulations like you show in this image, they reproduce what we see. And so we think we understand the physics of what causes this and why the universe has the appearance that it does.
Yep. And so we've gone 45 powers of 10 now. We're up at basically 5 times 10 to the 26th meters at 45 powers of 10 removed from quarks. And thinking to sort of wrap up with large numbers, Michael was just talking about superclusters with hundreds of thousands of galaxies. So when you look through the universe, we're talking hundreds of millions, perhaps a few trillion galaxies. Each one of those, the large ones, will have hundreds of billions of stars. And we're now pretty confident, based on observations in our own local neighborhood, most of those stars having multiple planets. So just multiply all that together on the back of an envelope, and there's a lot of planets out there.
For sure. Yeah, it's an exciting time. I mean, again, it's sort of the golden age of astronomy, right? With planets being discovered all the time, the search for life going on, understanding more about the universe on the largest scales. It's just an incredible time to be doing astronomy.
It really is. And it's an incredible time to be able to share it. And so we certainly, we will reopen our public programs here at Lowell Observatory when we can do so safely. We're certainly going to be probably phasing that in to make sure that everybody who comes and visits remains safe and healthy. Our Deputy Director for Marketing and Communications, Danielle Adams, is kind of behind the scenes of this broadcast, just checking to see if there's any questions. And here's actually not a question, Michael, but a comment maybe we can react to from Karen Malice-Clark. Hi, Karen. During these days when our lives seem constricted, it's a refreshing, powerful mental exercise to think on this scale. And I would certainly agree.
I totally agree. I think astronomy is great for perspective, right? And not to downplay the terrible things going on in the world, but it's good to get a little bit of perspective sometimes,
Yep. Philip Pariah asks, have we seen the equivalent of the Oort cloud around an exoplanetary system?
That's a good question. I'm not an expert in this. I believe that there's been some evidence. There was a star, Tabby star, right, that seemed to vary in brightness in really surprising ways. And I thought one of the arguments, and I don't know if it's still valid or not, was that you might be seeing sort of the equivalent of an Oort cloud blocking the light from time to time as different objects move in front. But that's all I really remember. I don't think anything like that's ever been observed directly. It's too we can't even see the Oort cloud in our own galaxy. In our own solar system. We just infer its existence.
Yeah, and we know from observations of our own solar system there are things that in principle should exist around other stars. So we've detected planets, but then there's the question of whether you can detect exomoons around the planets or some of these smaller objects that probably exist in those solar systems. It just becomes a phenomenally hard measurement. Jim Davies asks, do any of the coffee places in this series have internet sales to buy beans? And I think the answer to that question is yes. In fact, I believe I was looking on Matador's website this morning, and you can order stuff online. Let's see, Claire Gibson asks, why does red light pass most easily through interstellar dust?
Oh, that's a good question. And basically, the light is blocked most efficiently when it's comparable in wavelength. We think of light as waves to the size of the thing that's blocking it. So the shorter wavelengths of light, like the blue light, are blocked or scattered more efficiently by these tiny dust grains. And the red light, or infrared light in particular, even longer wavelengths, is able to pass through unimpeded and give us a better view, essentially.
Right. Now, Albert Smith has a very simple, trivial question. Could you speak on the Planck length and its relationship to the quantum world?
So I mean, well, I'm not an expert on this, but what the Planck length is telling us basically is, the whole idea of quantum physics, right, is that there's an inherent fuzziness to nature, and there's a limit to how deeply we can peer into the universe on the finest scales. And the Planck length essentially tells us what's kind of the fundamental limit to how small we can peer and see things clearly. And so it comes out of fundamental quantum physics, and you can define the length based on Planck Constant, things like that. But that's what it comes down to, is there's an inherent limitation with which we can clearly make out details in the universe. It becomes fuzzy on these sorts of scales, and we can never know precisely.
Right, and you mentioned the Planck Constant, which during the development of quantum mechanics in the early 20th century, that sort of emerges as the amount by which things like energy are quantized. It only exists in discrete quantities, and this is phenomenally tiny, right? We're all the way back at the other end of the scales. Question from Pagilza. How long did you say a dinosaur's day was?
Oh, if I remember right, it was 21 hours.
Yeah, right.
It was 3 hours shorter than today, basically. Sorry, because the Earth was spinning faster.
Right, and that's and this kind of thing is happening all around us in astronomy, right? The day is getting longer. The stars up in the sky are moving around. All the constellations are changing. But a lot of these phenomena happen on timescales so vastly beyond, our own mortal window that we don't sort of perceive it. But it's out there. We live in a changing, dynamic universe. And as I've hope we've showed you today, it's a universe of just an incredible diversity of size. Go away and ponder 10 to the 45th power. That's really quite something. So we're going to wrap up here. Remember, we are all shut down here. We are supported by our generous members and gratefully accept any donations to the observatory. Our member base has been incredibly generous over the last month, and we really appreciate it. And we are really enjoying bringing the marvels of the cosmos to you virtually. Thanks very much, Michael, for tackling a trivial topic like quarks to superclusters.
Sure, my pleasure.
Yep. All right. Well, thank you. Join us again next week for our usual Meet an Astronomer and Cosmic Coffee series. You can get all of the information about our live streams off our website. Until then, be safe and be healthy, and we'll see you.